Think we're live. Are we live? Yes, we are. Good morning, good morning, good morning. Good morning. Good morning. Welcome, welcome. All right, we should be live. I believe I posted in the stream. I did. We'll wait a few minutes. It's Friday. It feels great. Hope everyone's feeling great today. Who's out there? Hold on. Is there anybody out there? Good morning. Who's that? Is that Sarah? Good morning, Sarah. We got to test out the board. So today we're going to do more than one word. Today we have a place. Today is a place. So the place of the day is up on the board. Someone learned how to make lasagna. That's awesome. Went shopping online. That's nice. All right. Let's add a file. I have to do my obligatory GIF, however you pronounce it. I don't even know. Doesn't matter as long as you guys see the thing. It's coming. It's coming. Who's out there? Yes. Yes, I hope, Sarah, I hope you visited Roosevelt Island. Not sure where you live, but if you live in Astoria, it's actually not that difficult to get to. It's on 36th Avenue. So if you take 36th Avenue and you're walking west, you can hit Roosevelt Island. The bridge is very, very, very short. You're not really crossing a long bridge. And there's not much to do on Roosevelt Island other than visit a park. There's a really nice park there. So since most parks are closed, that's where I go to work out. So I used to go to a park. Where was the park? There are a few in Astoria that are really, really nice, but they're all closed. So that one, for whatever reason, has remained open. So I've gone there, and the view is it's pretty awesome. It's a great view. So you get a great view of Queens. You get a great view of Manhattan. It's really nice. So I would go there. So we're gonna wait for others to join us, Sarah. It's only you in the room right now. No one can say that they're running late because of train delays, right? Or traffic. Maybe web traffic, right? That could be a reason. So we're still waiting. We'll wait a few more minutes. There's only one of you in here. Is there an exam today, Sarah? Let me see. There might be an AP exam. I wonder if it's a big one. Let's see. AP exam. Let's see. Hold on. AP exam schedule. Oh, more people are showing up. there's legit one person in here right now. Oh boy. Okay. Today is comparative government and politics, AP statistics, Spanish language and culture. Who's out there? Good morning, Edgar. Welcome, welcome. All right, we're going to wait just a few more minutes and then I must move on. And this is the last topic that we're going to speak about. And then it's just going to be review, 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 review. So one more minute and then we'll begin. All right, more of you are out there. Excellent. 30 more seconds and that's it. Then we begin. Not wait anymore. All right, that's it. So, good morning, welcome. The board is alive, and we're going to cover the last section of this chapter. We're going to be looking at the periodic functions. Specifically, we'll be looking at today sine and cosine, or the graphs of those functions. So, what are periodic functions? So, many things in daily life repeat with a predictable pattern, right? Such as weather, tides, and hours of daylight. So this periodic graph represents a normal heartbeat. So things that are again repeating constantly with this similar patterns, if you will. What I think of, or what comes to mind for me, yes, the heartbeat is one of the obvious ones, but I'm sure you have more examples that you can think of. But I think of a metronome, or something that keeps time, right? Like the clicking, right? So like when you're playing music, the thing that keeps you in time, steady beat. They call it beats per minute. 1, 2, 3, 4, and that could represent something that's periodic for sure. But I'm sure, like I said before, that you can think of other instances, and if you do, please feel free to drop a comment so that we can check those out. So periodic function, but now when we're looking at it in terms of some type of equation, if you will. So here we have a periodic function, And here's what f of x equals to f plus x, or f of x plus np. X plus np. So this, it seems a little bit abstract right now. So for every real number x in the domain of f, every integer n, and some positive real number p, the least possible positive value of p is the period of the function. Bah. So a lot's being said here, but we're going to go into some of the details so that when we revisit this function, it's going to make a little more sense. So the circumference of the unit circle, right? Radius equal to 1, if we think about it. I'll write it on the board quickly. So we have 2 pi r. R is 1. So again, this is the circumference formula, what I just circled. But if our radius is 1, then we have this as a circumference, 2 pi. So the least possible value of p for which the sine and cosine functions repeat is 2 pi. Therefore, the sine and cosine functions are periodic functions with period 2 pi. And the following statements are true for every integer n. So sine of x is equal to sine of x plus n times 2 pi, and cosine of x is equal to cosine of x plus n times 2 pi. So values of sine and cosine functions. So as this angle s increases, right, from 0 to pi divided by 2. Don't forget the radian measure, right? 2 pi, the entire circle, 360 degrees. Pi, you chop that in half, 180. So if we're looking at pi divided by 2, it's just half of 180, or 90 degrees, and etc. You can go quarter of pi, and then that will be 45 degrees, etc. But some patterns take shape, right? So from pi, or how the graph is fluctuating, if you will. So from pi divided by 2 to pi, we're going to have a decrease in the graph. So I'm just looking at sine right now. From pi to 3 pi divided by 2, we're going to have another decrease. And then from 3 pi divided by 2 to 2 pi, we're going to be increasing. So it seems kind of abstract without the actual visual, and we're going to look at that visual now. So what I would recommend that you do is you go on Desmos. If you have your graphing calculator, you can do it, but I think Desmos does a good job. I'm going to try to find a picture of a graph of the sine function. I'm going to post it on our digital whiteboard. So for now, let me see if I can post links in the chat. Good morning, Kyle. So does this work? Desmos.com. I wonder. I don't think it does. So again, this is my first time using the chat to share links. So I think that's a colossal fail on my end. So I'm sorry about that. But that's the name of the website. So please visit that. And what I would do is type in sine of x. So I'm going to try to find that here. I'm going to post it. Right. This is good. Okay. I'm going to be uploading it in about a second. All right. So let's see here. Still on my graph or on the board. Let's see. So hopefully you see the following. I'm going to upload this picture. Here it is. Hold on. I hope you see it. It's going to be placed shortly. Tell me if you see this. I just need acknowledgement. So I just posted it up on the board. Can someone out there please acknowledge? Please acknowledge that whatever you see, or this graph, can be seen on your end. Hey, Leanna, good morning. So again, I posted or I shared an image on the board, and I just want to make sure that you can see it. So again, were we able to see it? I'm just waiting for you. So I shared again a graph and a visual on the digital whiteboard. I just need someone out there to confirm that it can be seen. Please confirm. Is there anybody out there? I hope it didn't freeze. Okay, can you guys hear me? Kyle joined the board. Okay, so Kyle just joined the board. So that I saw. So Kyle, since Kyle left the board and Kyle joined the board again. So Kyle, since you're now on the board, can you see the graph that I shared on the board? Oh, the whiteboard, yes, I see it, the graph. Thank you. Yes, so it's live, it's there. And this is, again, let me see. So this is the graph for sine. So if we go back to what we're looking at in the PowerPoint or what's being shared on YouTube, we can see now. If we look from 0 to pi divided by 2, and notice that they have the degree measure there. So we start to ascend, right? When we go from 0 to 90, when we drop from 90 to 180, we're still decreasing from pi or 180 to 270, which is 3 pi divided by 2. We're still decreasing, but then we go back up on our way to 2 pi, and then this pattern repeats itself. So it's going to be slightly different for cosine, and that I'm going to post also. So cosine, it looks somewhat similar, but the only difference is that it starts, hold on, that it starts elsewhere. So let's look here. So we'll do cosine graph, and I want you to check it out. Check out the comparisons. And again, you can see this through if you have Desmos. I would look at that. I would go to Desmos again. You can just type all this in, sine, cosine, and you can see they're kind of the same in terms of their shape. It just seems that one was translated or just shifted. Okay. So I'm going to just add the other one in now. So this way we can compare. And you can always zoom out so you can look at them side by side. Good morning, Josh. I hope I can do this. Ooh, it's one on top of the other. Not good. So let me try again. All right, so they're both there now. Please take a look. So again, they're shaped similarly. And you can zoom out to get the full picture. Maybe if you zoom out 5%. Or 50%, excuse me. You'll be able to see it pretty well. I'm on a PC right now, and this PC sucks. So if you zoom out, you'll be able to see both side by side. So as you can see, they're both quite similar. I think 50% zoom out, you'll see both. So where sine increases, cosine is decreasing, and then vice versa. And you can see that from the chart for the most part. But at some point, they're going to be increasing at the same time. So if we look here more closely, So this is the sine function. And again, x is being expressed in radians, but don't forget that pi is 180. Pi is 180, so if you want to convert that right away, you can do that, and you'll have the degree measurement. And don't forget y, the output. Again, that's the value. All right, that's the value of, if you think about theta, right? So you're looking at sine theta, and you're getting the ratio. All right, so if you're looking at 45, it should be radical 2 divided by 2. I'm just trying to think of the other ones. If you have the 60 and, or sine of 30, right? We have sine of 30, right? Sine of 30, or 180 divided by 6. And then we have 1 divided by 2. Right, remember, if that's the acute angle, and I'll do this here quickly so you can see, right? If we have 30, 60, 90, here's 30, acute, hypotenuse. I mean, we can look at this, excuse me. All right, so if we have the following, remember 30, if this is 1, then what we have here, 1/2, right? And then here we have radical 3 divided by 2. So hopefully you remember these rules. Excuse me. My mistake, that should be 60. Excuse me. This is 60 here. And this is 30. Don't forget that the opposite side from the shortest or the smallest angle, right, will be half the length of the hypotenuse. So again, this is more appropriate now. So that's why sine of 30 is half, because you have 1/2 opposite divided by hypotenuse. So hopefully this is coming back to you here, these values for x. So now if you look at the domain and the range, the domain is boundless, right? It goes from negative infinity to positive infinity, but the range is more restricted. So in this case, when we just have sine of x, our range is from -1 to 1. And if we look here, some more details. Graph is continuous, as we just mentioned, over the domain. The x-intercepts are in the form of n pi, where n is an integer. The period is 2 pi. The graph is symmetric with respect to the origin, so the function is an odd function. For all x in the domain sine of negative x, we're going to have negative sine of x. So we have an odd function. So going back to what period means. So the period is 2 pi. So think of it as that pattern. The pattern, right? So the pattern length is 2 pi. So when we start at 0, we go up, and then we go down, and then back up to 2 pi. That's a period length. So similarly here, cosine. Notice how it starts at 1, it goes down, and then it comes back up. So here, hopefully you can see my mouse. So it starts here, it goes down, and it comes back up by the time it hits 2 pi. So that would be our period length. And notice that the domain is the same, from negative infinity to positive infinity. And our range is from -1 to 1. So again, period length is the same. Graph is continuous over the domain. X-intercepts are in the form of 2n plus 1 pi divided by 2, where n is an integer. So that we'll look at in a little more detail shortly as we continue on in the discussion. And the graph is symmetric with respect to the y-axis. So the function is an even function. So for all x in the domain cosine of negative x, it remains unchanged. It's going to equal to cosine of x. So we have an even function. So if we look at this first example, it says here, graph y is equal to 2 sine of x, and compare it to the graph of y equals sine of x. So some things to consider, right? So we already know what happens when we have, so here we have x. So let's do it this way. So here's x. We know sine of x. And you have the chart, right? So we have 0, pi divided by 2. You can look back in the whiteboard. if you scroll or if you move around the whiteboard, you'll see the values. I'm just going to rewrite them. Here we have pi, 3 pi divided by 2, and then we also have 2 pi. But we know the values, right? When sine of x is 0, this is 0. When we are at pi divided by 2, at 90, it's 1. Pi is 0. 3 pi divided by 2, negative 1. And then back at 2 pi is 0. But now the difference is this. Now we have, I'll change the color, 2 times the sine of x. So we already know what the sine of x is. We have these values for these angles. So we're just going to multiply everything by 2. This is still 0. This becomes 2. This is 0. This is negative 2. And this is 0. But if we look at the graph now, so again, you should have something like this. And this is from the handout that I've given you. So if we go to the class stream, let me find it. It should be one of the last handouts that I've given you. So in the learning materials, let's see. Trigonometric functions is what it is. No. Degree, special right. Solving for exact. Right, so this is in solving for exact values and sine and cosine graphs. So it's related to that handout. So again, if you haven't already done so, this is all in the shared materials. So go to the solving for exact values, semicolon, sine and cosine graphs. So if you haven't done so, please look for that handout. Okay, and now we'll continue. So, right here. So if you have access to printing this, great. What you could do, I suppose, if you really wanted to interact with this graph, you could take a screenshot of it and then edit the picture and then draw directly on it so you can see that. That's an option. I have to put a graph in here, which I will do. So let me just get a blank. We'll do radian coordinate grid. Coordinate plane with radian measure. Just give me 1 second while I find this. So I would plot this right now. If you have access to, I'm going to plot it with you. I just have to find, I think this one will work for me. Okay. I hope it does. Yes, I think it will. It's kind of large. Let's see what happens. Okay. It's not working. Okay. Yeah, oh, I hate this. So anyway, so if we plot this, I'll show you the graph. So it looks something like this. So notice the original function, sine, y equals sine of x, but when we compare it to now this blue graph, so I only provided the positive n, let's say, with the angles, so with the domain, from 0 to, I think, 2 pi, that's what I provided. So the graph would look as follows. Clearly it looks taller. So when we're describing the graph as, compared to the original one where it's a little bit taller, we call that amplitude. Or it looks as if the graph has been amplified, or it appears longer, if you will, right? So something happened, like there's a spike. So amplitude of a periodic function. So this is what I'm going to describe to you now is the more mathematical term for it. But let me go through that, and then we'll apply it in real world. Excuse me, real world. So the amplitude of a periodic function is half the difference between the maximum and minimum values. It describes the height of the graph both above and below a horizontal line passing through the middle of the graph. So the middle of the graph in this setting is the x-axis. So we can think of it that way. But amplitude in real life is something getting louder. Louder. So my voice now is capable of producing some type of sound wave. But if I increase the volume of what I'm saying, so now if we were to record that, I'm not sure if any of you have experience recording audio. If you ever record a voice memo, you should do that. You should talk at the same pitch, but just change the volume. So you probably will see, I think the wave comes out red when you record, especially if you have the iPhone. There's a voice memo feature. Record the voice memo. If you speak loudly, the wave is like spikes up. So it looks something like this. So I'll draw this on the graph. So if this is, silence, so as you are talking, so as I'm talking now, you see something like this. It looks that way because the graph, or this sound wave, you can say that we've zoomed out, so we can't see the details. But as I get louder, as I get louder, as I get louder and louder, that wave is going to go up. So that is one of the best examples of amplitude, or it amplifies. Frequency now is different. That's completely different. So frequency we're going to look at. That now determines more with the vibration, so with pitch. So I'm not sure if you've ever seen like these slow motion videos. I know they've done this with many things, but with guitar strings, I forget, I have to look it up, but they do slow-mo. So you can see when a string is plucked, you can see that it's moving in a wave form, right? So when they do it slow-mo, it gives the impression that it's a lower frequency. And when you play it back, you've probably seen slow-mo videos where everything is like really like low and slow, right? But the reason for that is then that the frequency is lower frequency. So then the wave changes. But if you talk high frequency, if you talk like in a falsetto voice, I don't know if I want to do a falsetto voice right now. Let me think about it. It's going to sound terrible. But then the wave there'll be more waves. So in other words, the patterns that we see, and I'm going to get into that more now because it's kind of hard to explain just through audio. You need a visual here. So when we look at amplitude, so going back to this, so the amplitude you can find as follows. So the graph of y equals a times the sine of x, or y is equal to a times cosine of x, where a is not equal to 0, that's the identifier, or where we locate the amplitude of the graph. We'll have the same shape as the graph y equals sine of x or y equals cosine of x, respectively, except with the range of here negative absolute value of a and then the absolute value of a. So the amplitude is a, or the absolute value of a. So in other words, think of it as a coefficient for the function, for lack of better words. So the amplitude, whether it's negative or positive, we're just thinking about how tall this is or how it's impacted in absolute terms. So let's see. So that's impacting the height of the graph. But now when we look at how we're going to impact the input, right? So we have sine of x, but now I want to impact what's going on within x, right? So something like here, sine of 2x. Now things are going to change. So if you think about what sine of x is, right, and this is in the chart. So in our chart, I'm going to write this out again. So we have sine, we have 0, pi divided by 2, pi, sorry, we have we have what, 3 pi divided by 2 and then 2 pi. So what did we say again? This was 0. Here we had 1, 0, negative 1, and then 0 again. Right, so if we go back and look at our chart, but then what's going to happen here is when we have sine of 2x, right? How is this going to change? So this is where it gets a little bit more confusing, or just slightly. I mean, you could plug in 0 for x, right? And that will know the outcome. So this will be clearly 0. But then what about everything else? So now we have to look at it in a little more detail. So for this, I'm going to give you the table here so that you can see. So if we have sine of 2x, so I want you to think about the following. So no matter what the value of the amplitude is, the periods of y is equal to a times sine of x, and y is equal to a times cosine of x are still 2 pi. But now when we look at 2x, look at what's happening here. So we could plug in the following. So notice now the table has changed a little bit, right? So instead of just going right to 2 pi, or pi divided by 2, excuse me, after 0, we're now looking in between. So we're going up in increments. We're multiplying now by half, right? So pi divided by 4, pi divided by 2, 3 pi divided by 4. And then we have here pi. But we're actually going up by increments of 45 degrees. That's what's happening here. So then here we have 5 pi divided by 4. Here we have 3 pi divided by 2, 7 pi divided by 4, and then 2 pi. So hopefully when you see what's happening here, you should notice that we're stretching out the table, but look at what happens here. So we're just going to, I mean, we could evaluate or look at 2x, right? So we multiply the following. So 2x, right? So 2x, or 0 times 2 is still 0, but if we multiply pi divided by 4 by 2, we get pi divided by 2. If we multiply 2 times pi divided by 2, then we're at pi. So it's almost as if we're not stretching, but we're narrowing the graph a little bit, right? So I'm just going to copy these values so that you can see what's happening. So this should look familiar to you here. So let's see. 0, 1, 0, right? So look at what's happening from here to here. So this should be familiar to you up to here. Did I miss one? Hold on, I'm just looking here. Pi, right, 2 pi, 0. I think I'm off by 1. 0, 1, 0, negative 1. Yeah, I messed up. I messed up, folks, because I started in the wrong place. So let me just correct this quickly. I just have to shift everything. So that was my mistake. So sine of 2x is outside. Sorry. I know it's Friday. So basically this is what's going to happen. So again, this will still be 0 here, but we're shifting everything now. And what I'm going to highlight is something that you should have noticed from the table. So in other words, look here. When I highlight this, I'm going to change the color. I'll change it to black. Right, so that should be familiar to you. Right, that pattern we already saw. So that's the sine graph going up and coming down and then back up to where it starts. So that's a period, right? But look at the overlap here. So I'm going to go with this different color, purple. And when I highlight the purple section, the pattern repeats again. So if we look at it graphically, is there a graph of this? So basically it would look something like this. So I'm going to draw this on the graph. So this is going to be quite poor. So it would look like this. Let me erase. So we're still at 0, but from 0 to 2 pi, we have two instances of this wave. So from here to here is one instance, and then I'm just going to put another circle right above it so that you can see how it repeats. So one complete cycle occurs in pi units. So there is a frequency, right, of this cycle. So when we had it before, there was only one instance, or it appeared one time the cycle. So here it's appearing 2 times. So let's see here. So basically this is looking at this again, right? So in the graph, look at what happens. So this is just a little bit more detailed. So when we compare the other one, so this is again, the blue or the solid graph is with sine of 2x. The original graph is dashed, but you can see how it's much wider. But the blue one is appearing more frequently. And what's appearing more frequently? This pattern. So this deals with frequency, if you will. So when we look here, when we look at the period, right? So when b is greater than 0, the graph of y equals to sine of bx will resemble that of y equals sine of x, but with period 2 pi divided by b. So in other words, when we're looking at period, we want the length of a cycle. That's basically what period is referring to. So how long is a cycle? So in this case, when we're looking at y or sine of 2x, so y is equal to sine of 2x. So in this case, the b value is 2. So basically, when we do 2 pi divided by 2, the period is pi units, or from 0 to pi, if you will. So that's how long the pattern is. When we start at 0 and we go to pi, the pattern of sine going up, down, and back up again. So I know this is a little bit abstract. You know, it's a little hard to show this. I can definitely try to share a YouTube video that goes into this a little bit in more detail, but I'm also going to send you all of the slides by the end of today. So if we go back here, so I want you to look at this example. So notice here now, this is cosine, and this is the last thing that I'm looking at today. So if we look at cosine here, y equals to cosine of 2/3 x. So notice here we're looking at 2x, right? So it was greater than 1, this value of b. Now this value of b is fractional. So if you look at what's happening here, it's going to take much longer to complete one cycle of cosine. So the graph is getting wider. So it kind of relates to if you think about parabolas, right, or quadratic equations. So, right, if we have y is equal to x squared, and you have y is equal to 2x squared, y is equal to 4x squared, these graphs become narrower, right? But, or yes, narrower. But when we look at it fractionally, the graph will become wider. So it's the same concept. So when it's between 0 and 1, and we're looking at applying this to the trigonometric function like sine or cosine, the graphs will become wider. So again, that's when it's fractional. But when it's greater than 1, the graphs will become narrower, or you'll see that the period, time, or length is reduced. So hopefully that makes it a little bit clearer. So on that note, I'm going to share everything that I have today with you. I'm going to share the PowerPoint. For homework, you're just going to complete the review sheet. You're going to do all of it. And then we're going to start reviewing on Tuesday. So let's see if there's any questions out there. Good morning, Mamadou. I'm just looking at this now. All right, so what did we do today? We looked at sine, cosine graphs in some detail. We looked at period. We looked at amplitude. I mentioned frequency as well. So there's a lot of vocabulary within this section, or within the whole chapter for that matter. But now that we've gone through this, that essentially concludes this chapter, and it concludes the course. So we're done with learning new material. I'm going to send over some YouTube videos related to this. So if this was a little bit confusing, just check the stream. I'll have it there for you so that you can access and reinforce everything that we went over. I'm going to send you the slides for this entire chapter with all of the solutions. I'm trying to think what else. And the homework for tonight is just going to be to finish the review sheet. Maybe some of you already finished it, and I don't think there's much left to finish anyway. So it shouldn't be too daunting of a task to do. So we're going to begin reviewing on Tuesday. Tuesday will be a review. I'm just trying to think what else. The exam is still going to be that first week of June. Again, I don't know the exact date. They haven't shared that with me, but I would imagine, I'm hoping that it's going to be for that Friday. And what would that be, the 4th, the 5th? Let me see. Again, I can't predict. Yeah, the 5th. So I can't predict the exact date. I just know that they're going to release the exam that week. So I would definitely give you a heads up. I'm not going to give it to you like the day that it's released, but just know that it's going to be released that week. And most likely, if it is released that week, I will give it to you on Friday. So on that note, if there are no questions, have a great weekend, a long weekend. It's your first day off since winter break, and mine too. So I'm really excited. I need a day off. I'm sitting in this chair, in my quote office unquote chair. I've been sitting here every day for like 12 hours ever since March 20th. I'm tired. I'm tired of sitting down. So I'm going to enjoy this weekend immensely. I hope you enjoy it as well. On that note, have a good one. And I'll see you again on Tuesday. So again, we're meeting on Tuesday. See you then.